Every single year, humanity throws away over 54 million tons of electronic waste, enough discarded phones, computers, and televisions to build a wall around the entire Earth. Hidden inside this electronic trash lies a fortune worth over $62 billion in gold, silver, platinum, and rare earth metals that are often more concentrated than natural ore deposits. A single smartphone contains more gold than a ton of gold ore from most mines, while old computer circuit boards hold precious metals worth more per pound than many jewelry stores. So how do millions of discarded electronics get transformed from worthless trash into valuable metal resources? How does yesterday's broken laptop become tomorrow's gold bar? Today we're breaking down the incredible process inside one of the world's most advanced electronic recycling facilities, where over 300 tons of old electronics get completely dismantled every single day to recover precious metals that will live again in new products. Make sure to subscribe as we explore the fascinating technology behind mining urban gold deposits hiding in our digital trash. The journey begins at collection points scattered across entire regions, where consumers drop off everything from ancient flip phones to massive server computers that once powered the early internet. These aren't random donations. Each discarded device contains a carefully engineered mix of valuable materials that trained recyclers can identify and extract. Modern smartphones contain over 60 different elements from the periodic table, including rare metals that are becoming increasingly scarce in traditional mining operations. Collection trucks equipped with secure storage systems gather tons of electronics daily from drop-off centers, corporate cleanouts, and municipal collection programs. These specialized vehicles maintain chain of custody documentation for devices that might contain sensitive data while providing proper handling for equipment containing hazardous materials like lead, mercury, and lithium that require careful processing to prevent environmental contamination. When these massive loads arrive at the recycling facility, they face immediate security protocols designed to protect both data privacy and worker safety. Initial sorting separates devices by type and potential value, with trained technicians identifying equipment that contains the highest concentrations of precious metals versus items that primarily offer base metal recovery opportunities. Data destruction represents the first critical step for any device capable of storing information, because electronic recycling facilities handle equipment from banks, hospitals, government agencies, and corporations with confidential data that must be completely destroyed. Industrial shredders and degaussing systems physically destroy storage devices, while magnetic field generators permanently erase any remaining data traces that could compromise security. Manual disassembly begins the actual recycling process as skilled technicians systematically remove valuable components from complex electronic devices using specialized tools designed for efficient material separation. Circuit boards get carefully extracted because they contain the highest concentrations of precious metals, while batteries require separate handling due to fire and chemical hazards that could endanger workers or contaminate other materials. Component sorting divides extracted materials into categories that require different processing approaches, because recovery techniques for gold differ completely from those needed for copper, aluminum, or rare earth elements. Advanced sorting systems use a combination of visual inspection, magnetic separation, and density classification to achieve material purities that enable efficient downstream processing. Precious metal-bearing components undergo detailed evaluation using handheld X-ray fluorescence analyzers that can identify metal concentrations in seconds without damaging the components. These portable analysis systems provide real-time feedback that helps technicians optimize sorting decisions while ensuring that high-value materials don't accidentally end up in lower-grade processing streams. Battery removal and classification requires extensive safety protocols because different battery chemistries present unique hazards ranging from fire risk to toxic gas generation. Lithium-ion batteries must be stored in fireproof containers with temperature monitoring, while older battery types containing mercury or cadmium require special handling to prevent environmental contamination during processing. Plastic component removal involves identifying different polymer types that require separate recycling pathways, with some plastics suitable for direct reprocessing, while others need chemical treatment to remove flame retardants or other additives that could contaminate recycled plastic streams. Advanced plastic identification systems use infrared spectroscopy to distinguish between dozens of different plastic formulations in seconds, Cable and wire processing represents a significant material recovery opportunity because modern electronics contain substantial quantities of copper wiring with excellent recycling potential. Automated wire stripping machines remove plastic insulation while preserving copper integrity, while specialized systems can process fiber optic cables to recover both glass fibers and protective materials. The prepared electronic components now flow towards specialized processing lines designed for different material types and recovery targets. Precious metal recovery lines use chemical and thermal processes to extract gold, silver, and platinum group metals from circuit boards and connectors. Base metal processing systems focus on recovering copper, aluminum, and steel through mechanical separation techniques. Quality control throughout the disassembly process ensures that materials get properly classified and that hazardous substances receive appropriate handling. Environmental monitoring systems track air quality and worker exposure to ensure that processing operations meet safety standards while achieving maximum material recovery efficiency. Every step gets documented to maintain complete traceability from incoming devices through final metal recovery. The precious metal recovery process begins with industrial shredding operations that reduce circuit boards and electronic components into uniform particles small enough for chemical processing while preserving the metallic content that makes electronic recycling profitable. These aren't ordinary shredders. They use specially hardened cutting mechanisms designed to handle the tough ceramics, metals, and composite materials found in modern electronics without excessive wear. Particle size control is absolutely critical because chemical extraction processes work most efficiently when all material pieces fall within narrow size ranges. Screening systems separate shredded electronics into multiple size fractions, with particles larger than half an inch returning for additional size reduction, while dust and particles smaller than 1 millimeter getting collected for specialized processing that recovers even microscopic metal traces. Magnetic separation systems remove ferrous metals like steel and iron, using powerful electromagnets that can extract metallic particles from moving material streams with incredible precision. These systems operate at multiple stages throughout the process because even small amounts of iron contamination can interfere with precious metal recovery chemistry by consuming expensive chemical reagents without contributing to valuable metal recovery. Density separation takes advantage of the fact that precious metals are much heavier than most other electronic materials, using water-based systems that allow dense metal particles to settle, while lighter materials like plastics and ceramics float to the surface for removal. Advanced density separation systems can achieve metal concentration improvements of over 10 to 1, dramatically reducing the volume of material requiring expensive chemical processing. Air classification systems use controlled airflow to separate materials by weight and aerodynamic properties, removing lightweight plastics and paper materials that would interfere with downstream processing. These systems create precise air currents that carry away unwanted materials while allowing metal-bearing particles to fall into collection systems, achieving separation efficiencies exceeding 95% for properly sized materials. The concentrated metal-bearing material now enters chemical leaching processes that selectively dissolve precious metals while leaving base metals and non-metallic materials unchanged. Acid leaching systems use carefully controlled concentrations of nitric acid, hydrochloric acid, or specialized reagent mixtures that can dissolve gold, silver, and platinum group metals without attacking the underlying circuit board materials or other components. Temperature control during chemical leaching requires precision that ensures complete metal dissolution while preventing unwanted side reactions that could consume expensive chemicals or create hazardous byproducts. Heating systems maintain leaching solutions at exactly optimal temperatures, typically between 140 and 180 degrees Fahrenheit, while monitoring systems track reaction, progress through real-time chemical analysis. The leaching process creates metal-rich solutions that contain dissolved precious metals, along with various impurities that must be removed before final metal recovery. These solutions undergo multiple purification stages, including filtration, pH adjustment, and selective precipitation that gradually increase metal purity while removing unwanted elements that could contaminate final products. Chemical precipitation processes add specific reagents that cause dissolved metals to form solid compounds that can be collected and processed into pure metals. Different metals require different precipitation chemistry, with gold typically precipitated using sodium metabisulfite, while silver gets recovered through chloride precipitation. The timing and chemical concentrations must be precisely controlled to achieve high recovery rates without co-precipitating unwanted impurities. Filtration systems separate precipitated metals from processing solutions using specialized filter media that can capture particles as small as 1 micrometer while maintaining flow rates that enable efficient production throughput. The filtered solutions get recycled back into the leaching process after chemical adjustment, creating closed-loop systems that minimize waste generation while maximizing metal recovery efficiency. Electrolytic refining represents the final purification stage for recovered precious metals, using electrical current to deposit ultra-pure metals onto cathode plates while leaving remaining impurities in solution. Electrolytic cells operate at precisely controlled voltages and current densities that optimize metal deposition rates while achieving purities exceeding 99.9% for gold and silver recovery. Base metal recovery follows parallel processing streams designed specifically for copper, aluminum, and other common electronic metals that represent significant value despite lower per-pound prices compared to precious metals. Copper recovery uses specialized leaching chemistry that dissolves copper compounds while preserving other metals for separate processing streams, achieving copper purities suitable for direct reuse in new electronic products. Rare earth element recovery presents unique challenges because these specialized metals exist in very small concentrations but have extremely high values for advanced electronic applications. Rare earth processing uses complex chemical separation techniques that can isolate individual elements like neodymium, europium, and terbium from mixed rare earth concentrates, often requiring dozens of processing steps to achieve final product specifications. Quality control throughout metal recovery involves continuous chemical analysis using atomic absorption spectroscopy, X-ray fluorescence, and other analytical techniques that can measure metal concentrations at parts per million levels. Laboratory testing verifies that recovered metals meet industry specifications for purity, while environmental monitoring ensures that processing operations comply with discharge limits for chemicals and heavy metals. Waste treatment systems process all liquid and solid wastes generated during metal recovery to prevent environmental contamination while recovering any residual metals that might remain in waste streams. Chemical neutralization systems adjust pH levels of waste solutions while precipitation and filtration remove metal traces before treated water gets discharged or recycled within the facility. The recovered metals emerge from processing as high-purity materials suitable for direct sale to refineries, manufacturers, or precious metal dealers. Gold typically gets cast into small bars or granules with documented purity certificates, while silver and platinum group metals get processed into forms specified by purchaser requirements. These recovered metals often achieve purities and market values identical to metals from traditional mining operations. The final processing stages transform recovered metals into market-ready products that meet the exact specifications required by refineries, manufacturers, and precious metal markets worldwide. Gold refining operations produce bars and granules with purity levels exceeding 99.9%. Documentation that traces each batch back to its original electronic sources, and certificates that verify compliance with responsible sourcing standards that are becoming increasingly important to manufacturers. Silver processing creates products ranging from industrial-grade shots suitable for electronics manufacturing to investment-grade bars that meet London Bullion Market Association standards for precious metal trading. The processing flexibility enables the facility to respond to market demands, while maximizing revenue from recovered materials by producing the highest value products for each metal grade and quantity. Platinum group metal recovery focuses on palladium and platinum extracted from electronic connectors and catalytic components in some electronic devices. These extremely valuable metals require specialized processing that can achieve recovery rates exceeding 95% while producing materials with purities suitable for immediate reuse in new electronic products or industrial applications. Rare earth element processing produces concentrated materials that serve as feedstock for specialized refineries that further process these critical materials into the high-purity compounds needed for advanced electronics manufacturing. The facility can recover over 15 different rare earth elements, with some individual elements worth more per pound than gold due to their critical importance in modern technology applications. Quality assurance programs ensure that all recovered materials meet industry standards for purity, composition, and contamination levels through testing protocols that exceed requirements for primary mining operations. Multiple analytical techniques verify metal content while screening for trace impurities that could affect performance in end-use applications. Certificate programs provide complete documentation that enables recovered materials to compete directly with virgin metals. Environmental impact assessment reveals that electronic recycling prevents the mining of over 20 tons of ore for every ton of electronics processed, while reducing energy consumption by up to 90% compared to primary metal production. The facility diverts thousands of tons of hazardous materials from landfills annually while recovering valuable resources that would otherwise require environmentally intensive mining operations. Hazardous material management systems safely process the toxic components found in electronic devices, including lead from older circuit boards, mercury from switches and displays, and lithium from batteries that could create fire hazards if improperly handled. Specialized treatment processes neutralize these materials or convert them into forms suitable for safe disposal or beneficial reuse in appropriate applications. Economic analysis demonstrates that electronic recycling creates significantly more jobs per ton of material processed compared to traditional waste disposal, while generating valuable commodities that contribute to local and national economies. The facility directly employs over 200 skilled technicians, chemists, and support staff, while supporting additional employment in transportation, equipment manufacturing, and downstream metal processing industries. Advanced automation continues improving processing efficiency through robotic systems that can identify and sort electronic components faster and more accurately than human workers. Machine vision systems can recognize thousands of different component types, while robotic handling systems can process delicate items without damage. These automation advances increase processing capacity while improving worker safety by reducing exposure to hazardous materials. Research and development efforts continuously explore new processing techniques that can handle emerging electronic technologies and recover additional valuable materials from electronic waste streams. Advanced separation technologies promise to recover materials that current processes cannot capture economically, while improved chemical processes could increase recovery rates while reducing environmental impact. The circular economy impact extends far beyond individual facilities as recovered metals return to manufacturing supply chains, reducing dependence on traditional mining while supporting the production of new electronic devices. Many major electronics manufacturers now source significant percentages of their raw materials from recycled sources, creating stable markets for recovered metals while reducing the environmental impact of new product manufacturing. Global expansion of electronic recycling technology helps address the growing electronic waste crisis in developing countries where rapid technology adoption creates massive waste streams but limited processing infrastructure. Technology transfer programs share processing knowledge, while equipment manufacturers develop smaller-scale systems suitable for regional processing operations that can serve local markets. Innovation in processing technology continues advancing the field through developments in selective leaching chemistry, automated disassembly systems, and advanced separation techniques that promise to increase recovery rates while reducing processing costs. Future processing systems may achieve near-complete material recovery while operating at scales that make electronic recycling economically viable even for lower-value electronic devices. The facility processes over 100,000 tons of electronic waste annually, recovering enough precious metals to supply manufacturing operations for thousands of new electronic devices while preventing massive quantities of toxic materials from contaminating the environment. The operation demonstrates how advanced technology and environmental responsibility can create profitable businesses that benefit both the economy and planetary health. Consumer awareness programs help individuals understand the importance of proper electronic disposal while providing convenient collection options that maximize participation in recycling programs. Education efforts focus on the hidden value in electronic devices and the environmental benefits of recycling, encouraging consumers to view electronic waste as a valuable resource rather than disposable trash. Future developments in electronic design increasingly consider end-of-life recycling requirements, with manufacturers designing products for easier disassembly and material recovery. This design for recycling approach promises to dramatically increase recycling efficiency while reducing the environmental impact of electronic production and consumption throughout the entire product lifecycle. And there you have it, the absolutely incredible process of transforming millions of pieces of electronic waste into valuable gold, silver, and rare metals every single day. The innovation, environmental benefits, and economic potential of electronic recycling showcases how advanced technology can turn our digital trash into treasure while protecting the planet for future generations. What other recycling technologies would you like us to explore? Drop a comment below and let us know what you think. And don't forget to like, share, and subscribe to keep exploring more fascinating industrial journeys with us.